Welcome. So we're going to be graphing polynomial functions. I'm going to put each graph on a separate podcast. That way, if you need to break it up, at least you're breaking it up in between graphs. All right. So we're going to graphing a polynomial function. These are going to be our steps. So first, we're going to use the leading term to determine the end behavior. Right? I have the 4 different end behaviors written down, and I believe they're in your notes as well. Right, so here we can, if the leading term, the exponent is odd, right, the ends are going to go in different directions, right? And if the leading coefficient is positive, our end behavior would be f of x approaches negative infinity as x approaches negative infinity, f of x approaches infinity as x approaches infinity. It goes up left to right. If it's odd degree, but the leading coefficient's negative, right, it's going to be the reverse. It's going to go down left to right. So f of x approaches positive infinity as x approaches negative infinity. F of x approaches negative infinity as x approaches positive infinity. And a little sample graph is next to each one of them. If it's an even degree, right, then ends go up the same direction. If it's positive, then both ends will go up, and f of x approaches infinity as x approaches negative infinity, and f of x approaches infinity as x approaches infinity. If the leading coefficient is negative, then both ends go down, and then f of x approaches negative infinity as x approaches negative infinity, and it approaches negative infinity as x approaches positive infinity. We need to find all our real zeros, our x-intercepts. We set y equal to 0, and then we use one of our techniques. Make sure you show all of your steps. Factoring out common monomial. Once we do that, we'll have a quadratic to factor, or maybe we can do factor by grouping with a polynomial, something cubic. Right? Factor by grouping. We have synthetic and long division, and this is using the rational root test. Right? So right here on this one, we'll be using the rational root test. And then we have substitution, right? And for all of them, make sure you show your steps. We use the x-intercepts to divide the graph into intervals and choose a test point in each interval to graph. And those are our turning points. Turning points are always in between x-intercepts. When we were graphing quadratics, we knew where our turning point was. We found the vertex. There's not a vertex for these. We don't have a way to find the turning points by hand, and we want to be able to find those. Now, when we're finding the turning points, we are not necessarily finding the exact turning point, but we are finding the approximate turning point based on the information. And that actually will be more meaningful for understanding why there's a turning point, where it is, right? And good candidates for your turning points. For our turning points, whenever possible, our x's are going to be integers, right? Unless the distance between two x-intercepts is not going to be, an integer is not going to be possible, right? So for instance, if the distance between two x-intercepts is 1, right, there's not an integer between two consecutive numbers. We'll have to choose like a half, right? And you'll see what that looks like in a moment, right? So I do want you to approximate all of your turning points, right? And that's what you'll be doing until you get to calculus. And then we'll have the tools to actually find them yourself, right? Because we're going to do all this, we're finding it ourselves. That is much more meaningful in terms of understanding graphs. And then we're going to use any additional information like symmetry and turning points and multiplicity to graph the function. Multiplicity is going to be very, very important because that's going to tell us, do we cross our x-intercepts? Right, so let's go right to the first one, right after we go over just a couple more things on our comprehensive graph. So the most important features of the graph of a polynomial function are your intercepts, your x and y intercepts, your extrema, which are your turning points, your relative max and min points, and the end behavior. A comprehensive graph of a polynomial function will exhibit the following features: all x-intercepts, y-intercept, all extreme points, your turning points, and enough of the graph to exhibit end behavior. Plotting a few additional points and connecting them with a smooth curve helps us complete the graph. So if you don't feel you have enough points, you can always plug a point in to get another one to help you graph. But most of them we're going to find. We're going to calculate those out by finding our x-intercepts, our turning points, and our y-intercept. So first of all, let's now we need to consider our function. And so it is f of x equals x to the fourth minus x cubed minus 2x squared. Use the leading term to determine the end behavior. Right? So it's even degree, positive leading coefficient. Our end behavior, we know is f of x is going to approach infinity as x approaches negative infinity. And f of x will approach infinity as x approaches positive infinity. Our graph will look something like that, right? So that helps us make sure that we're drawing it in the right direction, right? So we're connecting the points in the right way, right? We're starting high and we're ending high. We're going to find all the real zeros here. Notice that we have a greatest common factor that we could factor out. Right? All of those are divisible by x squared. So let's factor out our x squared. Right? So our greatest common factor here is x squared. Right? And so when we factor out x squared, we have, oops, what I put an equals there? I meant to put a parentheses. Right? So if we divide x to the fourth by x squared, we have x squared. If we divide x cubed by x squared, we just have an x. And negative 2x squared divided by x squared is going to just be negative 2. So now we're going to factor the rest of our quadratic equation. Right? I would assume on these that you'll be able to factor them. Right? It's going to be rare that anything cannot be just factored. Right? So we're going to we're going to take a times c and multiply. And now we need two numbers that multiply to give us a times c, which is negative 2. Right? Just 1 times negative 2. And adds to give us our b term of negative 1. Right? So if they multiply to be a negative number, one's negative and one's positive, they add to be a negative number. The larger term's got to be negative, and 2 has only that as factors. That's it. Right? So 2 times 1, negative 2 is the only thing equals 2. We want negative 2, so it's going to be negative 2 times 1. And negative 2 times 1 is negative 2, and negative 2 plus 1 is negative 1. All right, so now we're going to factor this. We keep the x squared, and then we replace the negative x with a negative 2x and a positive x, and we keep the negative 2. The first two are a group, the second two are a group, and we set it, of course, equal to 0 because we're solving. Factor out a common factor, both divisible by x. X squared divided by x is x. Negative 2x divided by x is negative 2. And then the only common factor for x and negative 2 is 1. So we can factor out our repeating x minus 2, and we're left with x plus 1. We set those equal to 0. X minus 2 equals 0. Right, we'd add 2 to both sides. X is 2. X plus 1 equals 0. Subtract 1 from both sides. X is negative 1. Right, so now we've got our x-intercepts. But remember, oh, I'm supposed to do that down here. I left a space down here. And I think it looks just fine right where it is. So we'll just write it over here. X minus 2 equals 0. X is 2. X plus 1 equals 0. X is negative 1. We're supposed to have 4 solutions, and I only see 2. Right? This is x to the fourth. We need 4 solutions. Where are there 2 solutions? Don't forget you factored out x squared. Don't forget him. X squared equals 0. If we take the square root of both sides, x is 0. And remember, that counts for 2. Right? That's multiplicity 2. Right? So we go on to the next one. So we've got our x-intercepts. Right? We need to find our turning points. Your turning points are going to be always in between your x-intercepts. Now with the vertex for the quadratic was halfway in between your x-intercepts. Won't quite work that way for our turning points. So we're going to choose integer values. So put your x-intercepts in order from least to greatest. We have negative 1, 0, and 2. Now between 0 and 2, we choose 1. Right? That's the only integer there. We're not going to take a fraction. We're not going to take 7/8 to see if it's more extreme than we got when we plugged in 1. Right? And we're not going to take, something else. We're going to take that integer. but there is no integer in between -1 and 0. So then let's just take the halfway point, -1/2. You don't have to test every combination of terms you can come up with in between your x-intercepts. Right? Choose integer values or choose the best fraction if there is none. Right? And that will approximate our turning points closely enough. Right? So we're going to evaluate our function at x equals -1/2 and 1, so we plug in -1/2. Right? And we get, so you have -1/2 to the 4th. Right? It'll give us 1/16. And then we have -1/2 cubed is -1/8. You just cube the two numbers. And then -1/2 squared would be a +1/4. Right? If you raise to an even power, it's negative to an even power, it's positive. You raise a negative to an odd power, it's going to be negative. Let's simplify out those double negatives, and let's multiply that 2 by 1/4. So we have 1/6 plus 1/8 minus 1/2, because 2 1/4 is a half. All right, and now we need a common denominator. So it's got to be 16, because 16 divides into 16, and 8 divides into 16, and so does 2. Right, so we have 1/16 plus 2/16 minus 8/16. Right, notice that if you just, so 8 times 2 is 16, just multiply 1 by 2 and you got your numerator. 2 times 8 is 16, 1 times 8 means 8's your numerator. You add those together, you get -5/16. Right, so your function is going to cross the x-axis at -1, and then it decreases because that's a negative number. Right, so we have to cross the x-axis because there's only one solution there. This is multiplicity 1. So we cross, right, at -1. Right, and then since that's a negative number, right, this is the point -1/2, -5/16. Right. We're going to decrease to that point. And then, of course, we have to come back and increase, right, because we have to get back to our next x-intercept. Right? So this here is the point -1/2, -5/16. It decreases, right, because this was -1, 0. And then it has to come back again for 0, 0. And then we'll plug in 1, which is a lot easier to plug in than -1/2 is. So let's continue getting our points. So that one is pretty easy, right? So you have 1 to the 4th minus 1 cubed minus 2 times 1 squared. Well, that's 1 minus 1 minus 2, -2. Right? So after the function is going to touch the x-axis is 0, 0, right? Because this one here was multiplicity 2, because that was an x squared. And then it's going to turn back the other way and decrease between 0 and 1. And then, of course, it's got to come back to the x-intercept. Right? Because it has to go back to your last x-intercept. Once you've got back to your last x-intercept, you're going to use your end behavior to graph the rest. We also want to graph our y-intercept. So if you plug in 0 for x, of course you've got 0. Right? So since that makes sense, because 0 was an x-intercept, of course 0 is going to be a y-intercept. Now you might have found this to be a little tedious, right, in terms of the evaluating. 1 was no problem, but you can do something called synthetic substitution. I think I have it in your notes already. And I'm not going to go over it in much detail on this problem. I'll go over it in much more detail in a later problem. All right. And so the first way we were taught to evaluate a polynomial for a given value was direct substitution. Simply put, that means you plug that value into the expression and found the result. And come back. There's another method called synthetic substitution that will make evaluating a polynomial a very simple process. The process is the same as synthetic division. The last value, the remainder, is the value of the function for a given value of x. Because we know if it were 0, right, when we were actually doing synthetic division to factor, to solve, we knew if we got 0 as a remainder, then what we divided by was a solution, right? Because the value of y was 0. If we don't get 0, that's just the value of the function when we plug in that particular point. So I did change, I have it both here as a decimal and as a fraction in your notes here. And I also have the 1 in there, even though that one was pretty easy. Now you do have to remember you have to represent any missing terms with zeros. We have no x and we have no constant. So we'll replace those with 0. Right? And so otherwise we just represent the coefficients. So we have 1, -1, -2, and then we have the 2 zeros for the 0x and the constant. And we bring down the 1. 1 times -1/2 or -0.5 is going to give us -1/2. And then I need a common denominator. I'm going to go over the one with the fraction. So I can change -1 to -2/2. And then I add those together. I have -3/2. If I multiply, I'm going to have a positive 3/4. I think I just multiply the numerator, multiply the denominator. The numbers are a lot smaller, a lot easier to work with on the fractions than they were on the decimal. But I can't combine the 3/4 and the -2, but -2 is -8/4. If I add those together, I have -5/4. If I multiply, I'm going to have a positive 5/8. If I add, I still have 5/8. Now it's really easy. 5/8 times -1/2 is -5/16, and if I add, I get -5/16. With the decimal, we got -0.3125, and if you divide -5 by 16, you'll find you get -3.125. Right? So that I really liked that a lot better than plugging into the equation to substitute that way. I don't care which way you do it, but I do find this to be much easier. And if you don't like it, if you didn't like this for fractions, you probably didn't like plugging it in for fractions either. It really didn't make that much of a difference with the 1. It was so easy. But I want to show you you do get the right same number as you got with plugging in. Okay, again, you have to represent the x and the constant with zeros. You bring down the 1. 1 times 1 is 1. Add, you get 0. 0 times 1 is 0. Add, you get -2. -2 times 1 is -2. Add, you get -2. -2 times 1 is -2. Add, you get -2. And that's the same thing we got when we plugged in. Right? So it didn't save you much time with the 1, but it might save you some time with other values like the -1/2. So we now have all the points we need. All we need to do is graph them. All right, so we have our x-intercepts. We have -1, 0, and 0, 0. That one's multiplicity 2. Make sure you remember that. It's a good idea to write next to it. And 2, 0. We already have our y-intercept. Our approximate relative minimum, we have -1/2. So this is the same as -1/2. And this was -5/16. So -1/2, of course, is halfway. -5/16 is a smidge. That's more than a smidge. More than a fourth. So do your best to make that a smidge more than a fourth. So a lot of space here. And then the other turning point was at 1, -2, approximate turning point. So notice these are both relative minimum values. We have no maximum. Oh, yeah, I do have maximum value, but it's an x-intercept. We wrote the end behavior on the other page. We'll write it again over here. So f of x goes to infinity as x goes to -infinity, and as x goes to positive infinity, right? F of x goes to positive infinity as x goes to infinity, right? Because this is going to be W-shaped, which means you need to start high, right? And so don't start out too wide, right? But don't start out like, don't make a vertical line. So, but it does grow pretty fast. So I think we'd be fine starting right there, right? So we go through the x-intercept, we cross, and then get to the turning point. Turn, 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 turn. And this is another turning point because we touch and turn. So turn the other direction. And then turning point, turn, 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 turn. Go through your last point and just keep on going. Try not to get too wide, but that looks fine. All right, so our domain, of course, is always going to be -infinity to infinity. That's why I typed it in. The range, look at your graph, right? This one will not be that easy to find without the graph. All right, so notice our low point there at -2, and we do go through that point, and both ends are up, so it's going to go to infinity. And we're done. We've graphed our first one. All right, it only took us 20 minutes. We're going to graph another one in this podcast. So I'm going to end the podcast right now, and then come back and join me on the second one. All right, bye for now.